Hiya, Mr. Green here again, and I'm going to be delivering to you the third lesson in the forces topic for Key Stage 4, Year 11, and this is Physics, Lesson 3 to understand Newton's laws of motion. Success criteria: by the end of this video, we should be able to know and apply Newton's 3 laws of motion. So, first up, Isaac Newton, really famous scientist, born in 1642 and died in 1727, known as the father of modern physics. His study of mechanics culminated in the formation of the 3 laws of motion and is the basis of modern physics, which we still use today. You probably heard the story about the apple falling off the tree and onto his head, and him formulating ideas about gravity. And this relates to that. This relates to his Principia Mathematica, which he released, which detailed that. So Newton was really interested in motion, he was really interested in movement, and he was really interested in physics. And he came up with 3 laws of motion, which we're going to be looking at today. So we're going to look at the laws of motion, we're going to apply them to certain situations, and we're going to do some questions concerning those. So, Newton's first law of motion. Newton's first law is stated as such: an object will continue to stay at rest or move with a uniform velocity unless a force acts upon it. We can put that in simpler terms. In other words, objects will just keep on doing what they're doing until they are forced to change. So an object will keep moving until another force acts on it and stops it from moving. An object will move at the same speed until a force causes it to speed up or causes it to slow down. An object will remain at rest unless acted on by an unbalanced force. The football there is at rest and will remain at rest as long as nothing interacts with it. When the foot starts to kick the ball, that becomes unbalanced. When we get an unbalanced force, we get a resultant force. That resultant force causes movement. We've said earlier, forces are something that cause change. They cause a change in the movement of an object. And in this case, the resultant force will do so. An object in motion will continue with a constant speed and a constant direction, unless it's acted on by an unbalanced force. In this case, the football hitting the net, that provides a backward force to that. So, with seatbelts, have a look at that video. We can see the man and the car are both moving at the same speed, and the wall stops the car. So why does the man continue on? Well, when we talk about Newton's first law, we've said it will carry on doing what it's doing unless it's acted on by a force. The wall in this case is acting only upon the car, it's not acting upon the person. So there's no force pushing the person back. So Newton's first law states it will continue on at the same speed. This video shows us the same concepts occurring. When the car is stopped, the body inside the car continues on at the same speed. So again, why would a seatbelt help us with that then? Well, if we're not wearing a seatbelt, the body inside the car will continue to move at the same speed until it's acted on by a different force. The seatbelt provides that force. It provides another force pushing you back. So if we see the next video shows with a seatbelt and the person stops, the person doesn't go as further forward. So with that explanation given to us, using Newton's first law, can we explain why we should always wear seatbelts? Okay, so I'm going to ask you to pause now, give yourself 5 or so minutes to answer that question. Okay, here's the answer to that question. 5 possible marks, I'll go through each mark. So, the force of the road on the lock wheels provides an unbalanced force to change the car's state of motion. Remember, there's friction between the wheels and the road, and when we apply the brakes onto that, the force of the road provides an unbalanced force, slowing the car down. Or if it crashes into a wall, the wall provides that force. But there's no unbalanced force on the person inside the car. Only the car's experiencing that unbalanced force. So the person in the car will continue in motion, sliding along the seat forwards at the same speed as they were going previously. A person in motion will stay in motion with the same speed and in the same direction unless it's acted upon by the unbalanced force of the seatbelt. Seatbelts are used to provide safety for passengers whose motion is governed by Newton's laws, and the seatbelt provides that unbalanced force that brings you from a state of motion to a state of rest. Okay, so that's Newton's first law. We now come to Newton's second law. So Newton's second law is stated such: the acceleration of an object is proportional to the size of the resultant force and inversely proportional to the mass of the object. So on an object moving, it's got an unbalanced force, it will accelerate. The size of that acceleration is dependent on how big the force you apply and how much the mass is. The bigger the mass, the lower the acceleration. The higher the force, the bigger the acceleration. Bit of a mouthful, so we can express this much simpler in the form of an equation, and that equation is this: force is equal to mass times acceleration. Force is measured in newtons, mass in kilograms, and acceleration in meters per second squared. Simply, we can say this is F equals ma, force equals mass times acceleration. Now in the examination, you'd probably get a question which relates to something size or mass. So we'll do a quick example. A car's got a mass of 1,000 kilograms. What force must the car's engine supply to cause an acceleration of 2 meters per second? Well, we know force is equal to mass times acceleration. The mass in this case is 1,000 kilograms and the acceleration is 2. So it's simply a case of replacing that into our equation. 1,000 times 2 giving us 2,000 newtons. Again, when you come to do this in the examination or anytime you answer it, make sure you write out all the steps of your calculation just to ensure you get those full marks. Okay, I'm going to leave 3 questions on the board for this bit. If you pause it and attempt all 3 sets of questions, you will need to convert some of these and you will need to rearrange the equation. So pause the video, take yourself a few minutes to answer those questions and unpause when you're ready for the answers. Okay, question 1. Calculate the force applied if the mass of 10 kilograms accelerates at 12 meters per second. Well, simply force equals mass times acceleration, F equals ma. We put these into our equation, so mass is 10 and acceleration is 12. Multiply those together, force is 120 newtons. Again, write all my steps out and ensure my units are in there. B, a mass of 500 grams accelerates at 20 meters per second. So we've got force equals mass times acceleration, but mass needs to be in kilograms. At the moment it's in grams, so we need to convert it into kilograms. To convert grams to kilograms, we divide by 1,000 milligrams. Sorry, grams are a lot smaller than kilograms. 1,000 grams in a kilogram. Once we've done that, we have 0.5. 500 divided by 1,000 gives us 0.5. That's our mass in kilograms. Just replace those in the equation now. That's 0.5 multiplied by 20 gives us 10 newtons. Question C, a mass of 4 kilograms accelerates at 0.4 kilometers per second. So again, force is mass times acceleration. But look quickly at that. We can see that acceleration needs to be in meters per second squared, and it's not, it's in kilometers per second squared. To convert kilometers per second to meters per second, we multiply that by 1,000. That gives us 0.4 times 1,000, which is 400. Now got all the figures we can put into our equation. That would be 4 times 400. Mass is 4, acceleration is 400. That gives us 1,600 newtons. Okay, question 2. Calculating the mass this time. So we need to rearrange the equation to make mass the subject. So if force is mass times acceleration, we rearrange it, take the acceleration over to the other side of the equal sign, it becomes divided by. So mass is force divided by acceleration. Now we've got that equation, we can attack these questions. So question 1, a force of 15 newtons causes an acceleration of 4 meters per second. In this case, mass is force divided by acceleration. So we've got 15 divided by 4. Just replace those in the equation simply. 15 divided by 4, 3.75 meters per second squared. Again, make sure you get those right units. B, a force of 100 millinewtons causes an acceleration of 0.2 meters per second. So we've got force divided by acceleration, but force needs to be in newtons. It's currently in millinewtons, so to convert, we divide by 1,000. 100 divided by 1,000 is 0.1. So the mass would be 0.1, which is the force, divided by 0.2, which is the acceleration, 0.5 meters per second squared. And C, a force of 3 newtons causes an acceleration of 400 millimeters per second. So mass divided equals force divided by acceleration, but again acceleration needs to be in meters per second. Convert millimeters per second to meters per second by dividing by 1,000. 400 divided by 1,000 is 0.4. 3 divided by 0.4 gives us 7.5 meters per second squared. And finally, acceleration. So we need to rearrange the equation. If force equals mass times acceleration, acceleration is force divided by mass. First one, 12 divided by 3 gives us 4 meters per second. Second one, force divided by mass, but force needs to be in newtons. Currently in kilonewtons, so convert to newtons, times by 1,000. 3 times 1,000 is 3,000 newtons. That would be 3,000 then divided by 3, which is our mass, 1,000 meters per second squared. Again, C, force of 12 newtons applied to a mass of 30 milligrams. Force divided by mass. Mass needs to be in grams. We convert it to grams by dividing by 1,000. 30 divided by 1,000 gives us 0.03. 12 divided by 0.3 gives us 40 meters per second squared. Okay, Newton's third law. So Newton's third law is a force cannot exist on its own. There is always a second force acting against it. So it states if object A exerts a force on object B, then object B exerts an equal but opposite force on object A. You'll have heard this put more simply as for every action there is an equal and opposite reaction. Forces do not exist in isolation. If there is one force being applied on objects, there will be a second force applied away from the object, onto the object that's applying the force in the first place. Forces happen because of interactions between objects, and we call these action-reaction pairs. So the two forces are always the same size, they act in opposite directions, and they act on a different object. Let's have a look at an example. So the examples here, a block of wood sits on rest at a tabletop. That's the diagram there. We've got our piece of wood with the weight acting down, the force acting up. So we're looking for two action-reaction pairs in accordance with Newton's third law. So our first one would be the force of the table on the wood and the force of the wood on the table. So we've got the normal force acting up. There must be an equal and opposite force, and that's the force of the wood on the table. Our second pair would be the force of the earth on the wood, causing the weight. Now we know if there's a weight being caused, there needs to be an equal and opposite reaction. So there's the force of earth on the wood, and there's the force of the wood on the earth, which again is an equal size but in opposite directions. Test yourself using this one. These are simple true or false statements. Again, pause the video, read through them, and answer whether you feel they're true or false using Newton's third law. Okay, for the answers then. So, David and Ruth are pushing on each other's hands and neither person's moving. There's no overall force there. No resultant force. So, right, true, T next to the statements that are true, F next to false. The size of the force acting on David is less than the size of the force acting on Ruth. Well, that's false. Newton's third law says these are always the same size. The size of the force exerted by David is the same as the size of the force acting on Ruth. Completely true. That accords with Newton's third law. David exerts a bigger force on Ruth than the force that Ruth exerts on David. Just said. Those forces will be equal, so the answer is false. Ruth experienced a bigger force than David. False. They experience the same force. Ruth and David exert forces of the same size. Completely true. Newton's law states that. Newton's third law states that those are equal. And here comes the second part, opposite. The force exerted by Ruth is in the same direction as the force exerted by David. That's false. Again, equal and opposite. So G, the forces exerted by David and Ruth are opposite in direction. That's completely true. Okay, so that was a really quick run through Newton's three laws. There'll be more to do in lessons, and there'll be exercises in booklets that we'll be giving out. There's loads of videos to watch on YouTube as well that explain these with loads more examples. Have a search out for them and have a look. Hope this has been useful. Review all the videos that you can on the school website to ensure that you're getting everything you can out from this. Okay, thank you very much. Goodbye.